So the next talk is by Damiano, Abram, and a bunch of people that you should trust about an algebraic framework for silent preprocessing with trustless setup and active security.
Yeah. So hi everybody, my name is Damiano, and now I'm going to present our paper, which is titled "An Algebraic Framework for Silent Preprocessing with Trustless Setup and Active Security." This work has been accepted at Crypto this year, and it is the result of a collaboration between myself, Ivan Damgård, Claudio Orlandi, and Peter Scholl. So the main contribution of our work is the introduction of this algebraic framework for silent preprocessing, and in particular, it can be used to build two-party homomorphic secret sharing for branching programs and public key PCFs for OT and vector OLE. In the paper, we present instantiations of the framework. The first one is PAILLIER, following the blueprint of Orlandi et al. And Roy et al. Works of last year. The second one is a variant of the Joey-Libert crypto system. And the final one is class groups. This last option has also a very nice property, namely that it doesn't need trusted setups. All the other solutions instead do. In the work, we also explain how to upgrade all our constructions to active security, obtaining implementable solutions. And all these solutions work in the generic framework. Okay, our starting point is the rise of PAILLIER. It is a paper by Orlandi et al. Presented at Eurocrypt last year. And in their work, the authors came up with a very interesting technique to perform D-logs in a distributed way with minimal interaction. So they work in the two-party setting over a PAILLIER group. There is this RSA modulo n of unknown factorization, and the group Z and square star can be rewritten as the product of the subgroup generated by 1 plus n, where D-log is easy, and another subgroup H, where D-log is hard. We have two elements, alpha and beta, whose quotient is guaranteed to be 1 plus n to the m for some integer m, and we give alpha only to A and beta only to B. The technique presented in the rise of PAILLIER allows the two parties to obtain a secret sharing of m modulo n without any interaction. So the parties just need to work on their inputs. So how did the authors of the rise of PAILLIER achieve this? Well, in order to understand what is going on, we have to rewrite alpha as alpha 0 plus alpha 1 times n, where alpha 0 and alpha 1 are integers smaller than n. We take the red equation, the one that you see in the top left, and we rewrite it as alpha equal to 1 plus n to the m times beta. So the authors of the rise of PAILLIER noticed that if A and B reduce their inputs modulo n, they obtain the same value, and this value is clearly alpha 0. Why is this the case? Well, we can look at the black equation on the left. We can reduce both sides modulo n, and we notice that 1 plus n to the m vanishes. It just becomes 1. So the parties end up with the same value. The second fundamental observation in the rise of PAILLIER is that alpha, beta, and alpha 0 all belong to the same coset of 1 plus n. So it's clear that alpha and beta belong to the same coset because we can obtain one from another by just multiplying by a power of 1 plus n. The question is why alpha 0 belongs to this coset too. And the reason is the following. So you can look at the element at the bottom of the slide. That element belongs to the coset of alpha 0. And using a well-known trick on the PAILLIER group, we can rewrite it in that way. Then using the distributive property, we obtain alpha 0 plus alpha 1 times n, which is actually alpha. So this is the proof that alpha belongs to the coset of alpha 0, since alpha does, also beta does. So how can we use these facts to obtain a secret sharing of m without any interaction? So A and B own these two values on the same coset of the group generated by 1 plus n. We represent the coset as a circle because the underlying group is cyclic. A and B both know this value alpha 0 belonging to the coset. They obtain it by reducing their inputs modulo n. Once alpha 0 is known, obtaining a secret sharing of m without any interaction is easy. The parties just need to compute a D-log of the quotient between their input and alpha 0. Okay, in our work, we generalize these techniques to a generic framework. We call the problem that we solve the NIDLS problem, and it stands for non-interactive discrete log sharing problem. Again, we work with two parties, but not over the PAILLIER group, but over a generalization. So we have a group G that is the product of F and H, where F is cyclic. Furthermore, we require that D-log is easy over F, but hard over H. We denote the order of F by T, and we have two elements, alpha and beta, whose quotient is F to the m. We give alpha only to A, beta only to B, and the problem is to obtain a secret sharing of m modulo T without any interaction. So in order to solve this problem, we introduce two new notions. The first one is called the coset labeling function. We take our group G and we represent it in this way. So each of these circles is a different coset of F in G. We represent them as circles because F is cyclic. A coset labeling function is just a function that maps each of these cosets into a different element. We denote the function by pi, and we ask that is computable in polynomial time. The second concept that we introduce is called the lifting function, and basically it does the opposite of the coset labeling function. It takes an element in the image of pi, and it maps it into one element of the corresponding coset. We denote the function by delta, and again, we ask that it is computable in polynomial time. What are the properties of these two functions? Well, if we first apply delta and then pi, we end up in the same element we started with. But if we do the opposite, that's no longer true. If we apply first pi and then delta, we may obtain another value, but this value belongs to the same coset we were at the beginning. Okay, how do we use these two notions to solve the NIDLS problem? A and B have these two elements belonging to the same coset, so they can locally apply pi on their inputs, obtaining the same element in the image of pi. Then they can lift this element back to the coset using the lifting function. The result is called gamma, and it is clearly known to both parties. Once gamma is known, obtaining a secret sharing of M non-interactively is easy. We just use the same techniques that we used for PAILLIER. Namely, the parties perform a D-log of the quotient between their input and gamma. So to summarize, coset labeling functions are sufficient to solve the NIDLS problem non-interactively. Okay, there are many groups G that can be rewritten as the product of F and H, where D-log is easy over F. The question is, how many of these groups have coset labeling functions? We came up with some instantiations. The first one is PAILLIER. Actually, this is nothing new. It is our starting point. Here, pi is just the reduction modulo n, whereas the lifting function just is the embedding of Zn star into Zn square star. Another case in which we have coset labeling functions is when the group F is small, namely it is polynomial in size in the security parameter. Here, the coset labeling function is just the one that outputs the minimum in the coset with respect to the lexicographical order, and we can compute this efficiently because the coset is small. We can just list all the elements because there are polynomially many of them. And the corresponding lifting function is the identity. By combining this trick when F is small with the Chinese remainder theorem, we are also able to equip some variants of the Joly-Libert cryptosystem with coset labeling functions. In this variant, the plaintext space has size that is the product of the first L primes for some integer L. And okay, also this setting is good for our framework. The final instantiation, and probably the most interesting one, is class groups. Here, pi and delta are homomorphisms, and actually they are not new to cryptography. They were, for instance, used in the nice cryptosystem. The good thing about class groups is that we can generate the parameters of the group without any trusted setup, whereas Joly-Libert and PAILLIER always need this trusted dealer that generates an RSA modulo of unknown factorization. Okay, this is how we solve the NIDLS problem, but how do we use these techniques to obtain silent preprocessing? The trick is not new. It was already known since the rise of PAILLIER. We just generalize it to our framework. I will present now the trick over PAILLIER because I need it later, and then I will say a few words about how to generalize it. So we have these two parties A and B that work on the PAILLIER group and has a known factorization, and we denote the decryption key by D. This is just an integer that is congruent to 0 modulo phi of n and congruent to 1 modulo n. We assume that the parties have a subtractive secret sharing over the integers of y times d, where y is any value in the integers. We also need a public PAILLIER ciphertext C encrypting another value x. So by locally raising the ciphertext to their share of y times d, the parties are able to obtain values alpha and beta whose quotient is 1 plus n to the x times y. You can easily verify the computation in the center of the slide, but basically what we are performing is a distributed decryption of C using the shares of y times d. The only difference is that everything is also raised to y. Anyway, the important point here is that alpha and beta satisfy the condition to apply the NIDLS techniques because their quotient lies in the subgroup generated by 1 plus n. So without any interaction, the parties are able to obtain a secret sharing of the product X times Y. So to summarize, if we have a subtractive secret sharing of Y times D and a random PAILLIER ciphertext encrypting a value X, the parties are able to non-interactively obtain a secret sharing of X times Y. Okay, now we want to generalize this idea to our framework, but we cannot rely on PAILLIER anymore because the security of PAILLIER relies on DCR, and well, DCR may not hold in our framework. So we need another crypto system, and we use Algebraic. Why Algebraic? Because it has some nice homomorphic properties. It has a rather simple decryption algorithm. And for the security, we just need to require that D-log is hard over H, which is something that we are already asking. We assume that the parties have a public Algebraic key. So there is this element G sampled from the group using some distribution D. And then we have H that is a power of G. We keep the exponent secret, and that will be our secret key. Now we need two subtracted secret sharings over the integers. The first one is the secret sharing of a value Y. The second one is a secret sharing of Y times S, where S is the secret key. We also need a public Algebraic ciphertext encrypting a value X. And yeah, using the same techniques that I described before. So this distributed decryption of the ciphertext plus the NIDLS techniques, the parties are able to non-interactively obtain a secret sharing of X times Y. Okay, we use these techniques to build homomorphic secret sharing for branching programs. So what's HSS? HSS is a particular secret sharing scheme that allows to homomorphically evaluate functions on secret shared inputs, obtaining secret shared outputs without any communication. The function needs to belong to some class supported by the scheme. In our case, the class is a generalization of branching programs. To some extent, HSS can be regarded as some version of homomorphic encryption in which we don't protect the privacy of the inputs through encryption, but through secret sharing. All right. How do we build HSS? Well, we just plug the techniques that I described before into the construction of the rise of PAILLIER. Everything is pretty straightforward. I won't explain the details here because of a matter of time. The second cool thing that we build is public key PCFs for OT and vector OLE. I will just present the vector OLE construction because it's simpler and it uses the same technique as the OT one. So a PCF stands for a pseudo-random correlation function. And basically it is a tool that generates large amount of correlated randomness with minimal communication. We want to tackle vector OLE correlation. So we have two parties. We work over a group Zn, and we provide B with a random element Y. Our goal is to provide A with a random pair XZ and B with a random element W. And these values have to satisfy the correlation rule you see in the middle, namely that W is equal to Z plus X times Y. Clearly, we want that no information about Y and W is linked to A, whereas no information about X and Z is linked to B. We want to generate many tuples of this kind. We call them vector OLE tuples, and we want also minimal communication. In particular, we want complexity that is sublinear in the amount of tuples we produce, and we want only one round of interaction. The parties just send one small message, and then they have all the vector OLE correlation that they need. The tool for doing this is called a public key PCF. Basically, the parties just send a small public key, keeping the private counterpart secret. In order to generate a vector OLE tuple, they just pick a public random nonce, C, for instance, using the random oracle. And then they can evaluate the nonce with the two public keys and their own secret key. A obtains X and Z, B obtains W, and the outputs are guaranteed to satisfy the correlation rule in the middle, namely that W is Z plus X times Y. If the parties want another vector OLE tuple, they just pick another random nonce using the random oracle, and they repeat the operations. Okay, public key PCFs for vector OLE were already known since the rise of PAILLIER. In that work, they have this construction that can be split into two parts. The first one is a PCF that relies on a trusted dealer, and then we have a one-round setup that substitutes the trusted dealer. Both constructions are based on this distributed D-log technique on the PAILLIER group, the one that I described at the beginning. And the one-round setup has a disadvantage, namely that it still relies on a trusted dealer that generates an RSA modulo of unknown factorization. So our goal now is to move this construction to our framework so that using the class group instantiation, we can finally get rid of this setup once and for all. Okay, I will start from the PCF with a trusted dealer. I will just catch it because of a matter of time. So we have the two parties that work on the PAILLIER group. We represent the decryption key by D. The setup provides the parties with a subtractive secret sharing of D times Y over the integers. And Y here is the vector release secret, the one known to B. The nonces of the construction are random PAILLIER ciphertext. They will encrypt the value X of the vector release correlation. And we can generate this ciphertext using a random oracle because every element in Zn square star is a PAILLIER ciphertext. So we can just pick a random element in Zn square star. Now, the parties have a subtractive secret sharing of Y times D, and they have this PAILLIER encryption of X. So we can use the techniques that I described in the previous slides. And so the parties obtain a secret sharing of X times Y without any interaction. And the two shares are exactly W and Z, the values that we are looking for. Okay, this is the construction over the PAILLIER group. Can we move it to our framework? The answer is no. The issue is we are not able to sample Elgamal ciphertext using a random oracle. That's because the second element of an Elgamal ciphertext belongs to the group generated by the first element and F. And if our group is not cyclic, for instance, class groups are not cyclic, it's impossible for the random oracle to produce such an element. Okay, so what's the summary? The summary is that our PCF with trusted dealer cannot be moved to the generic framework. We still need to rely on PAILLIER. But this is not totally a bad news because the problematic part of this construction is the one-round setup. That's the part that needs this RSA modulo of unknown factorization, actually. So maybe we are still able to move this one-round setup to our framework, and then using class groups, we can get rid of the trusted dealer. This is what we do, and we actually succeed in it. So what's the goal of this one-round setup? We have to provide the parties with the subtractive secret sharing of D times Y. D is the decryption key. It is actually known to A. A will generate the RSA modulo of the public key PCF with trusted dealer, the construction that I just described. Y is the vector release secret known to B. Essentially, this is a one-round OLE protocol. So it can be used also in other cases. Okay, we use exactly the same construction of the rise of PAILLIER, but we move it to our new framework. We have this CRS made of two elements, G and C, sampled from the group using the distribution D. The parties just send one message. A sends this value V, that is G to the R times C to the D, where R is random. B sends instead an Elgamal-like ciphertext encrypting its input Y. The public key of this ciphertext is the one encoded into the CRS, in particular this value C. Using some local computations, the parties are able to compute some values alpha and beta, whose quotient is F to the Y times D. And at this point, we can use the NIDLS techniques to obtain a secret sharing of D times Y without any interaction. And this is exactly what we want. So to summarize, we have a one-round protocol and in our generic framework. And if we use class groups, we can get rid of the trusted setup because the CRS, G, and C can be generated using a random oracle. The question is about security. So one could argue that the element V sent by A leaks no information about the decryption key because there is this element G to the R that hides all the information. Whereas the message sent by B leaks no information about Y because it's an Elgamal ciphertext. So under DDH, there are no issues. But this is true only if C is uniformly distributed over G, the group generated by G. And here we have issues because class groups are not cyclic. So we cannot generate a C uniformly over the group generated by G using a random oracle. If we pick two random values, most likely they belong to different cyclic groups. Furthermore, we cannot even argue that C looks like a power of G. And that's because we want to rely on a trustless setup. So the parties will obtain the randomness that was used for the generation of this CRS. That randomness is the output of the random oracle. And the bad news is that for class groups, the distribution D is not invertible. So if I give you a sample, you are not able to retrieve the randomness that produced it. So in the security proof, if you want to substitute C with the power of G, we are not able to simulate the randomness that produced that C. So we need to come up with something new. And this is a new assumption. It is called the XDH, and it stands for decisional cross-group diffie. It basically says that if we have a tuple GC, the randomness used to produce G and C, G to the R and C to the R, then this is computationally indistinguishable from a tuple that has exactly the same form, but we substitute G to the R with a random power of C. This assumption is sufficient to prove the security of our protocol, and it can also be used in other applications over class groups. For instance, we use it to prove the security of Pedersen commitments over class groups that don't need a trusted setup. There were other papers that claimed this result, but those proofs were bugged. We really need the XDH. Okay, this is the end of my presentation. Here there is a slide with the summary of our results. And yeah, I thank you for the attention.
Questions?